The last function we're going to look at, the last Laplace transform we'll see in this section, is a special function called the impulse function, sometimes called the Dirac delta. Dirac, named for Paul Dirac, physicist. So the impulse function is a special function that we'll see an example in a minute of a problem where something is struck by a hammer at one moment. So this idea of being struck in a moment and kind of focusing a force on one instant in time and having nothing else besides that, the impulse function is what we use to model that. So the impulse function is kind of an unusual one. Basically, it's zero everywhere except for at one point, and then at that one point we assume that it's essentially infinite, meaning that it's just very large compared to everything else around it. So for all practical purposes, we assume that it's just essentially infinite. Again, we could do the Laplace transform by formula with this, but I'll just go ahead and tell you what the Laplace transform is in a second. So you can have the Dirac delta, the plane function by itself has an impulse at 0, and then of course you can shift it like we have before to some point A. So the more general delta function is delta of t minus a, and it's 0 everywhere except at a, and then at a it's, again, quote unquote infinity as far as we would like it to be. What's interesting to us at the moment is the Laplace transform, and this Laplace transform is the easiest one that you'll see. The Laplace transform of the delta function, the plane delta function, is just 1, and then if you shift that delta of t minus a, that's e to the negative as. Again, you could use some of the other Laplace transforms we've developed to look at that one. Now, this rounds out the entire Laplace transform formula sheet that you'll find on your test. We've seen all the formulas now. There's nothing on there that we haven't covered yet. And so we're just about done. I'll just show you one example quickly using the impulse function, and that will wrap up everything that we're going to do with Laplace transforms this semester. So here's an example of a physical situation. So say we've got a spring at rest, and then that spring gets struck by a hammer at t equals 0. So the problem starts with a spring struck by a hammer, and then it starts vibrating. So that strike, that impulse, is the forcing function. There's just a single impulse and then no other forcing action on the spring. The spring just vibrates as long as it will. Now I haven't told you anything about the spring, but I'll set up the differential equation, and you should be able to tell from this that the mass we're looking at is 1, the damper, there's no damping on this one, so it's undamped, and then the spring constant is 1 also. So I didn't write that down, but the mass is 1, the damping constant is 0, and the spring stiffness constant is 1, just to make life easy, to kind of show you how it's going to work. If we change those constants, it wouldn't change dramatically, just change the values that we use as we go through the problem. Also, we're going to assume that it was at equilibrium. If it was sitting at rest, the initial position was 0, and the initial velocity was also 0. So it wasn't moving, it was at rest, at its equilibrium, and then it's struck by a hammer. And let's see what happens. So to do this, we're going to use Laplace transforms, obviously, since we're looking at that section. So the Laplace transform everything, the second derivative becomes s squared times x minus s times the initial value of little x minus the initial value of the derivative. So both of those are going to go away since they're both 0. And then minus the transform of x equals then the transform of the delta function. Again, that's just 1. It's the simplest one. So the two middle terms go away. We just have x times s squared minus 1. Plus 1. S squared plus 1. So x equals 1 over s squared plus 1, which, if you're looking at your Laplace transform table, you should see that the Laplace transform of sine of t is 1 over s squared plus 1. So x of t is just sine of t. So this one would oscillate, again, forever because there's no damping. But it would start at 0, and it would begin to oscillate according to the sine function. So it's just a simple example using the impulse function, the Dirac delta. It's, again, relatively simple because the Laplace transform is so simple, and combining that with the things we've done before, there shouldn't be too much that gives you trouble with the impulse function.